Welcome back, folks, to the University of Kansas Physics Colloquium. Today we have Paul Cazeaux from the University of Minnesota. He did his PhD in 2012 from the University of Paris 6. He did a postdoc at École Polytechnique Lausanne, and then he's been a postdoc at the University of Minnesota since then. He'll talk to us about geometry and the design of van der Waals 2D heterostructures. Dr. Cazeaux.
Thank you very much. Thank you for the invitation. So I will talk to you about some work that we are doing at the University of Minnesota, actually in a bigger group that I will present that includes physicists, in particular at Harvard University, and a bunch of people. And we are trying to understand, model, and ultimately predict some properties of these heterostructures that I will talk to you about. So I would like to start my talk by a quote from Feynman, who in 1959 in his lecture, there is plenty of room at the bottom, somehow said something related to these atomic layers that we actually play with. So what could we do with layered structures if we had just the right layers? What would be the properties of materials if we could arrange the atoms the way we want them? And when we have some control of the arrangement of things on a small scale, we will get an enormously greater range of possible properties that substance can have and of different things that we can do. So this was somewhat prescient. I don't know if Feynman actually thought about all these different things that we do nowadays, but it turns out that we have actually isolated two-dimensional materials, materials that are just one or just a few atoms thick, and we are starting to play really with the arrangement of atoms at this atomic scale. So just a short history here. It started actually badly for 2D materials. So in the 1930s, Landau and Piles predicted that long range in two-dimensional systems could not be possible. And then in 1966, we actually had a theorem that was proved by Mermin and Wagner saying that we could not expect to have long range order in two-dimensional systems. So that sounded quite badly, and that actually killed a little bit the field for a few decades. And people didn't really look because it was thought this structure would be unstable because of fluctuations due to temperature. Then in 1997, a little bit an unrelated observation is that so Professor Geim started by levitating a frog and won the Ig Nobel Prize for this in 2000s. And then just a few years after, in 2004, with Professor Novoselov, they actually isolated freely standing graphene. So the story is now classical. We actually can isolate graphene just using Scotch tape and ripping off little flakes of graphite, ripping off layers of graphene, basically by sticking just usual 3M Scotch tape, and then repeatedly ripping it apart until we can look at this layer of Scotch tape and discover that we have isolated graphene. So this is how it worked. And for this discovery, they got a Nobel Prize in 2010. And in 2013, we had this $1 billion investment by the European Union. So the field of graphene really steamed on. And what I want to say is that actually there is a lot beyond graphene, which has been the wonder material, which has been studied intensively for the past 15 years. We have actually discovered a lot of other materials, which are also two-dimensional. Not all of them have been actually realized in the lab, but they are thought to be stable. So we have hexagonal boron nitride. We have this transition metal decalcolgenides. Yes?
So is the theorem wrong?
The theorem is not wrong, but the reason people suspect that it's actually possible to have order is that it's not strictly two-dimensional. The layers can ripple, for example, a little bit, and this actually invalidates the theorem. So this kind of three-dimensional effect, even though the geometry is really two-dimensional. All right, so what does graphene look like? So it's this hexagonal structure of carbon atoms that is on the left. So on a two-dimensional plane, it has a lattice constant of 2.46 angstrom and very nice properties, sometimes wonderful. So it's a semi-metal with this Dirac cone, linear dispersion that makes the electron behave a little bit like photons. It has extraordinary properties like unheard of mechanical strength, conductivity of both electricity and heat. and all around, really an interesting material to study, but it has been really studied to death, even though we are discovering still new things in interactions. But actually, it's not the only one. So just an example is hexagonal boron nitride on the right, where we break this symmetry of having just carbon atoms by introducing atoms of boron and N. And as you can see, it has a slightly different lattice constant of 2.5 angstrom. And both of these structures are really stable. They are really two-dimensional, and all the bonds in plane are fully occupied. And this means that we can potentially put them on top of each other and start to play with such structure, which by having just a very little interaction between the two. So in particular, we know that hexagonal boron nitride is actually a very good insulator, a dielectric. It's very stable. So what we can do is, if we want to probe what graphene does and protect it from the environment, we can stick it in a sandwich of boron nitride. And this way, because boron nitride doesn't do very much, our layer of graphene is kind of isolated, and we will be able to study it as if it were freestanding, in some sense. So here is our the state of the field. We have this cornucopia of 2D materials that have all different properties that we can imagine. So we have metals like graphene, we have insulators like boron nitride, but we also have semiconductors like molybdenum disulfide. We have some superconductors, and with this richness of new 2D materials comes the question: how about now we combine them, we put them on top of each other, and we try to predict the properties, and in the end, to have the properties that we are interested in. So this is an image from Professor Cazeaux that actually illustrates a little bit like what we are trying to do. Unlike when we stack, say, conventional materials on top of each other and they have to bond at the interface, these 2D materials have very little need for bonding at the interface, only van der Waals forces. And this means that they don't tend to stick together in a periodic fashion. They just tend to be stacked in some kind of, like this stack of rocks. So we don't really know what angle we will achieve. And in the end, it poses a lot of problems because some conventional wisdom that we know about condensed matter systems will not be true in this case. So what is our goal with all of this? The dream would be to replace the current technology for semiconductors, for example. So we know that we are reaching the limits of what semiconductors can do in design of new processors. Intel is having a lot of trouble to go thinner and smaller. I think the current step is already 2 years behind. And getting thinner is getting to the range where actual quantum effects start to be important. And therefore, we have to take those into account. And our dream is with these 2D materials that we can really control at the nanoscale, be able to produce the right properties for the right devices of the future. And our challenge as computational scientists, mathematicians, or physicists would be to guide the exploration of these materials, because there is such a rich parameter space that there is no hope to just explore all properties by experiments. So we would like to be able to tell the experimentalists, this is what we want. Well, the experimenter will tell us this is what we want, and then we will say, okay, well, you could look at this particular combination in these particular parameters, and then try to see if it matches our computations. And we will look at these 2D materials that were launched also by Professor Geim and his collaborator Grigorieva, with this kind of misleading image where you see these 2D materials stacking on top of each other like Legos, whereas the reality is more like this picture of rocks that I was showing before, where the materials really do not stack like Legos. They actually are kind of randomly arranged, and this complicates the picture. So this effort is undertaken by this large team of people, which is under a Moiré grant, so covering a number of universities. So we are in the mathematics department at Minnesot, working in close collaboration, in particular with physicists at Harvard, in the group of Professor Cazeaux and Professor Kim in experimental physics. We also have engineering with Professor Tadmore at Minnesota, Delaware with Professor Pletschak, and I want to mention our external collaborators, so in particular Eric Kantzes, who's really a great help, someone who has a lot of experience with models in condensed matter and in quantum mechanics, like density functional theory, and a lot of insights into how to do these things. So I want to start off a little bit easy and looking at a particular phenomenon that appears precisely because of this weak interaction between the layers. If we, so this is an experiment from the group of Philip Kim, where so Hyobin Yu looks at what happens if you have two layers that are really have a very close twist angle between the two. So I have two layers of graphene that are on top of each other with an extremely small angle between the two. Here it's 0.8 to 0.2 degree. Here it's not quite as uniform. But what we see is that when we look at it with just the right tools, so in this case a complex method of electron diffraction coupled with some dark field imaging, then we see that we have a pattern of domains that will appear. Domains that have a slightly different nature at a very large scale. This bar over here is 500 nanometers. It's far, far above the atomic scale. And what we see is that we have this kind of regular pattern that appears. So what is it? This is kind of an explanation of what is the Moiré pattern in terms of small animation. So if I have two lattices that have the same lattice constant on top of each other, they are both hexagonal lattices, and we have a twist angle between the two, then we see with a naked eye kind of a pattern appearing. Right? So we have these loops over here, and we see that the distance between them changes as the angle changes. And this gives us a length scale, which is the Moiré length scale, which is not quite periodic, but really quasi-periodic, and which depends on the angle, and especially at small angles, it's inversely proportional to the angle. So with this mechanism, we can produce structures that are quasi-periodic, almost periodic, on a very large scale. So at this scale of, if we think about 0.1, 0.2 degrees, then we can really reach gigantic, not quite periodic, but quasi-periodic domains. How do we understand this? So a very simple, very classical model is that of the Frankel-Kontorova model, which was studied in particular by Aubry and Le Daéron. And this model models what happens when we have a frustration mechanism, something where we have two competing length scales. So we have a chain with elastic bonds, so we can think about a chain of atoms spaced regularly with little springs in between them. And this chain is then placed into a periodic potential, which has a different periodicity. So at rest, if there is no external potential, this chain will just be consisting at minimum energy of equidistant atoms separated by this lattice constants L. But when we introduce this external potential, there will be a competition. These atoms will try to move a little bit towards the nearby Waals. But at the same time, they have to minimize their energy, their elastic energy. And this competition will lead to a strong dependence on actually both length scales. So here the ratio between this length scale associated with the periodic chain and the lattice constant of this external potential. And we can actually study this and see that we will have a modulation of the chain that can be of two natures. So if the external perturbation is small enough, then we will have a smooth perturbation. Basically, the atoms will move a little bit in a smooth manner. And that means that if I take this chain over here and I pull from one side, then the chain will just follow very nicely. However, if I increase this potential over here, at some point, the atoms will basically all be sitting in the Waals, and there will be some forbidden positions. The atom cannot sit on the top of the Waals. And therefore, as I pull, I need to impart some finite amount of energy, the so-called Peierls-Nabarro barrier, in order to pull the chain. And in practice, this looks like having some kind of local discommensurations where we have the atom sitting periodically on the bottom of the Waals, and then somewhere there is an atom missing or something like this, and this is very localized. So now we can think about applying this to our picture of the Moiré pattern. So there are some very quantitative models that have been put out already on this kind of problems where we try to model the atomistic relaxation. And the idea is the same that I was explaining before. So we have now two layers where one layer is sitting somehow in the potential created by the other layer. And so it will try to relax towards the positions that are preferred. So in particular, we have a misfit energy. Some staggering configuration are preferred. If I think about the hexagon on top of the other hexagon, it's better to have one of the atoms sitting in the middle. It's nicer over there than having the two perfectly aligned. So the two perfectly aligned are these AA configurations. They have a lot of, they are much more unfavorable compared to nicely staggered configurations like this, where the two lattices are staggered, and they really like this kind of position. And so when we introduce this misfit energy and we make a competition between elastic energy inside each layer, which doesn't like to be modulated too much, but nevertheless it tries to optimize the overall energy, then we get patterns like this, where we have these triangular patterns between the AA sites that are really unfavorable. Here we have these regions where we get the nice staggering, the favorable staggering over a large spacing, a large domain, and then between those domains we see actually transition regions which look like walls, and this compares to the picture I was showing earlier, where we have these domains where large domains where we have perfect alignments, and in between them we have these walls arranged in a triangular pattern. So now, given that we know how to make an atomistic model and we can compute this kind of pattern, how do we know how to validate this prediction? And here we are looking currently at what happens when we look at the diffraction pattern, which is another way. Yes.
Sorry.
Yes.
Back to that picture. Could you go back to that?
Yes.
Can you make a continuum model of two fields that show behavior like this? Avoid all the atoms.
You can make a continuum model. This is usually how these multi-scale models work. However, near these AA regions where there is high amounts of displacement, actually.
It look like solitons or something.
Yes, a little bit. So the soliton would be this, these domain walls over there.
Continuum models exist for these double layered things. So
We are thinking about it.
It's a very elementary deal. If you have two types of atoms,
Yes.
and then you have springs between them,
Mhm.
and you go to a continuum, you'll have two branches with optical and acoustic photons.
Yes.
So there's a continuum rendition that eliminates all the complications of the atomistic picture.
Sure.
Those things exist here for these.
Yeah, I mean, you can make a simple, as you were saying, continuous model.
Yeah.
The problem is not going to be very accurate because we don't know how to parameterize it. That's the problem here. So the question is how to validate a model. Once we have a prediction, we want to validate it, and we look at the diffraction pattern as a way to compare information at the microscopic level. So this here would be the diffraction pattern of this bilayer I was showing earlier. And what we will see is that we have these big peaks over here. So that's the substrates, just stronger peaks. We can forget about them. What's interesting is the tiny peaks next door that follow this hexagonal pattern over here. And when we zoom on those, we see that we have the important thing is to look at these two main peaks. So those come from the rotation of two diffraction patterns of rotated layers. That will give me two peaks slightly rotated compared to one another. I could compare the angle between the rotations by looking at how far these peaks are apart. But then I also see satellite peaks that come from the relaxation. And I can compare that to my prediction just by taking the Fourier transform of this pattern I was simulating earlier and see if I'm predicting something that looks reasonable. So here we see, for example, that we have the right peaks. The simulation seems to pick up at least the right peaks. However, over here, it's clear that the middle peak is not quite as strong in experiments as it is in the simulation, and therefore there is actually hope. So this is not a bad result. This is a result that tells me that there is information in the diffraction pattern that can be exploited to validate a model. My model was very rudimentary. If I had just the right result, I would be very worried, because then that would mean there is no way to validate anything. If any reasonable model gives me the right pattern, then there is no information to be exploited. However, here I see that I have a small difference, and therefore I could look into the real questions. Is my model picking up on the right symmetries? Is there any symmetry breaking in the actual experimental results? Something I didn't introduce in my model. And And there will be a lot of questions also about these Moiré patterns in general. In particular, are they stable at room temperature? Do they have any effects on the electronic properties of the materials? Things that remain to be investigated. So, a very interesting result that has been realized in the Moiré patterns is that the Hofstadter butterfly has been observed in experiments. So I will try to tell you a little bit about what is the Hofstadter butterfly, and I need to take a little detour through two basic concepts of condensed matter. So first of all, we want to introduce magnetic fields in our materials and to measure what happens when we put a magnetic field. So we look at what happens to electrons in two-dimensional systems when we introduce a magnetic field which is perpendicular to the layer, pointing up. Then we can write a simple Hamiltonian. There is no lattice here. Everything is just a free electron. And this theory is very well known. We know that this is actually translated into some kind of harmonic oscillator. And therefore, the energies are quantized into levels that are multiples, integer multiples plus 1/2 of a given frequency, cyclotron frequency, which depends on the magnetic field over here. And we know that these orbits will contain flux quanta given by h by c over E. And also, we also have a given magnetic length scale, which is given by this quantity over here, the square root of h bar over EB. And so when we look at the energy levels, in this picture, when we have a free electron moving through these magnetic fields, we see that they get quantized into levels that are massively degenerate. There is a huge amount of electrons occupying each level over here. And this is the basic picture. Now, a very different problem is when we look at an electron moving through a periodic potential. So this is the theory developed by Bloch. We write a simple Hamiltonian, which writes as including now periodic potential U, where the lattice constant is this A over here. And we know that the eigenstates, the eigenmodes of this particular Hamiltonian will look like Bloch waves, that is, periodic modulations of plane waves. So K, here the wave number, will be a main parameter, and then it picks up the information from the lattice into these wave functions U and K that are periodic. And so when we look at the Bloch wave, it will look like a periodic modulation that corresponds to this K parameter. And then we also have this periodic, with the periodicity of the lattice, smaller oscillations that corresponds, for example, to localization of the electrons around the atom. And so when we look at the energy landscape, this time it's composed of energy bands that are continuous, possibly with gaps in between. And so two very different pictures, where in one case we have this discrete sequence of energy levels, and here we have this continuous series of bands. Yes?
What is the value of the K? The K continuous or not continuous?
I'm sorry?
The K.
Yes?
Allowed value of K.
K is contained in between.
Continuous or not continuous?
Yes, it's a continuous parameter.
Okay, I don't think so, but I'm not going to argue with you now. Go ahead.
All right. So now, what happens if we put these two pictures together? We want to look at what happens at an electron, which is in a square lattice, so two-dimensional, with a magnetic field and with a periodic potential. And this was plotted out in 1976 by Hofstadter, the result of this looking at the energy levels of the Hamiltonian. So it can be written also at the Harper's equation. And what is important as a parameter is to look at the lattice and figure out that now we have a flux of the magnetic field through a given unit cell of the lattice. So that would be just BA squared in this case. And so the ratio between this unit flux quanta phi naught that comes in the Landau theory and the flux that comes through a unit cell is going to be an important parameter. It comes in the Harper's equation, and it translates basically the fact that we here have, again, two competing length scales. One is the lattice periodicity, the other one is the periodicity coming from the cyclotron motion of the electrons in the magnetic fields. And this competing length scale gives the rise to this fractal structure that is plotted out here. So we have the flux of the magnetic field as the x-axis, and the y-axis is given by the energy. So we plot out the energy levels of the Hamiltonian for a given flux. We see in particular at flux equal to 0, we just have a continuous line. If the flux is 1, we again have a continuous line. 2, so for integer values of this flux, we have just this continuous line corresponding to the fact that the system is actually periodic. However, in between, we have this splitting and this beautiful fractal pattern that appears. Now, observing this has been a long-standing goal in the physics, condensed matter physics community. The problem is that to reach actually integer values or values that are not too small of this parameter b, if you want to have the periodicity here to be the periodicity of an atomic lattice, would need absolutely gigantic magnetic fields, something which is not realizable in practice. And so this was long just a dream because we could not have periodicities that are large enough to really probe this kind of pattern. So one thing that was tried is to make artificial periodicities, but this never quite worked out because you couldn't get that to be precise enough to get the right results. However, because of this Moiré pattern that introduced this larger periodicity, this Hofstadter butterfly was spotted in 2013, almost simultaneously by the group of Philip Kim and the group of Herrero at MIT. Due to the presence of the Moiré superlattice. So it's a little bit difficult to see in those pictures because they are not quite directly related to the Hofstadter butterfly. But what we are interested in is the repetition of the pattern as we reach rational values of the ratio of fluxes, the flux of the magnetic field in a unit cell of the lattice, and the flux defined by the Landau levels. And we see here this kind of repetition. This is the work of Philip Kim in bilayers of graphene on top of a layer of boron nitride. So the boron nitride has a slightly different lattice constants. This provides us also with a Moiré pattern. This is what is probed here. Here, this is just a monolayer also on top of boron nitride. This also introduces a Moiré pattern on which we can probe the Hofstadter butterfly. So what we can see here in blue, tracing the rays that appear in the experimental results over here, are the fans, the Landau levels that will appear just in graphene itself. But then the red additional rays that appear because we have here an integer value, for example, of the ratio of fluxes over here or here, for example. These come from the repetition from this Hofstadter butterfly. So this was an interesting application of these heterostructures. And we can also look at what happens when we put now a bilayer of graphene with a tiny twist angle between the two. When we look at the magnetoresistance data, we will see also an interesting behavior. So this is the direct conductivity, and this is over here the whole transverse conductivity. So we apply an electric field in this direction, and we get conductivity, conductance in the other direction. And so what is interesting is to look at these satellite insulating states. So we have the usual bottom of the Dirac cone for the graphene. That makes it so that there is very little conductance in the middle. But here, these states left and right come from the opening of gaps due to this superlattice. So now I want to go briefly a little bit about another application of 2D materials, which is surface plasmon polaritons. So the interest of plasmons is we want to manipulate light at a nanoscale. The problem here is that due just to the wavelength of light at any reasonable frequency, if you are at a nanoscale, this is now a huge wave, and there is no way to manipulate light. Plasmonics are kind of the dream of reaching very high frequencies at very tiny wavelengths. And this can be done because the plasmons, I will show in a couple of minutes, actually have extremely small wavelengths compared to the free space wavelength of light at the same frequency. And so they enable us to strongly localize these electromagnetic fields and control the energy, which is the electromagnetic energy, at sub-wavelength scales. So in particular, applications would be nano antennas, building optical or electrical circuits that really have an extremely small and extremely fast scales. All right, so a traditional plasmon appears at the surface between a metal and a dielectric. So in the metal, because we have free electrons, we can start to have free oscillations of the charge over here. And of course, these oscillations of charge will create, in response, an electromagnetic field associated with it. So here, the electric field connects these charges just by the Coulomb potential, for example. And so the coupling between this electromagnetic wave that is created and this oscillation of the charge is precisely the plasmon. So it's a evanescent wave. It will not survive very long either in the dielectric or the metal. So it's strongly localized around this interface. And it will have a very small wavelength. Now, there is a lot of losses that are due to the metal. And so, as in, for example, in semiconductors, we try to make things thinner to minimize losses. So the thinnest we can go is, instead of looking at a bulk metal, we can look at a two-dimensional metal, something which is a pure interface. So this is a two-dimensional metal over here, a sheet that is coming out of the plane of this screen. We have these oscillations of the charge, and they are coupled to an electromagnetic wave outside. And this is described, sorry for a few equations here. So we have very simply here Maxwell's equation in the free space. And we can describe what happens here by having an effective surface conductivity. So that will allow charges and currents to be created on the surface. And so the physics tells us that the electric field should be, the tangential component of electric field should be continuous, going through the layer, whereas because of the induced currents, due to this oscillation of charges, the magnetic field, the tangential component of magnetic field will see a jump, which is linked precisely by this effective surface conductivity. And now, the condition to observe a plasmon is that the imaginary part of the conductivity is very large compared to the real part. So this is not, of course, usually the case. It's a resonant condition where we have reached a point where the electrons resonate with the rest of the electromagnetic field. So here is, for example, a simulation done by Matthias Meyer at the University of Minnesota. So it's a finite element simulation. We represent the electrical field in such a plasmon, which is excited by a small dipole position just above the layer. So here the layer is represented by a line, which is like this, coming out of the plane. We see the rest of the wave, the electromagnetic wave, going through space, absorbed by absorbing boundary conditions on the sides of this the simulation domain. And then on the interface, we can observe the plasmon with very high oscillations of the electrical field. And the more interesting things to see here is that we effectively see that the wavelength of the plasmon is much, much smaller at a given frequency than the wavelength of the wave in the free space. So this is what is so exciting. Now the crucial ingredient to make these plasmons happen, as I was saying, is to engineer the conductivity to have just the right frequency, the right behavior at the right frequency. So how do we compute or predict this kind of properties? Usually we have to go to a very detailed description of the system. So this is done looking at density functional theory simulations, for example. And we can look at these plasmons at resonances of the electrons as we impose electrical fields. So we have to look at the microscopic dielectric functions, which is this operator, epsilon minus 1, depending on a given wavelength and the wave number. So as we impose a total field, we want to know what is the applied field that we have to give for this total field to appear. So this is the result of this computation over here. We have the total field, phi, out of which we subtract the reaction of the material, create some charges. Out of these charges, we can extract what is the potential created by these charges. And so now we have subtracted out of the total field, we subtract what the reaction of the material creates. If this reaction is 0, then that means we do not have to apply any external fields for this disturbance to exist. This is the definition of a resonance. So if we find the zeros of this dielectric function, which can be computed from the DFT, then we will identify the plasmonic response of the material. So this has been done, for example, for graphene over here. So we know that in a frequency range, which is a terahertz, so in below infrareds, we will have a plasmonic response, which is damped if we look to too high frequencies, so high frequencies. And what is interesting is to look at the ratio of the wavelength in the air and the wavelength in the material itself. And we see that this ratio is about 200 to 100. So we have a factor of 2 orders of magnitude between the wavelengths in the free air and the wavelength of the plasmon. This is what plasmons are all about. Now, what we have been working a little bit on is how to engineer plasmons that have even higher frequency, so optical range in particular. And this, we predict, will happen if we actually put, for example, a system of 2 layers of graphene, like here, and we dope this system very highly by putting some lithium in between the 2 layers of graphene. So by putting lithium, which gives a lot of electrons to the system very readily, we push the Fermi level very high, and this doping will produce very different response to the electromagnetic fields. And in particular, using DFT calculations, what we have predicted is that there will be plasmons appearing and with a reasonable lifetime in the optical range. So just an application where we are able to predict some interesting properties of the material using the tools of density functional theory in this case. So we'd like to do that for more things. Yes?
Sorry, I can't read the figure. What doping concentration you are looking at when you say the extreme doping? What kind of concentration you are looking at?
So I think it's a maximum that is stable by the density functional theory calculations, which would be 2 lithium for each square root of 3 supercell. So I'm not.
It was done early, right? So people tried already to interpolate like sodium or lithium into graphene or graphite.
Yes.
So, but I was not really impressed with like how high can it go. So is this just theory or say experimental?
So this paper is theory, but it's connected to experimental results in the group of Philippe Kim, where they are trying to push this really high.
Right. So do you remember like how high you really want to go? Because you know the current state of ours is like 10 to the 13, right? So it's hard to go beyond that so far.
I'm not sure.
But there's more to a calculation of the dielectric constant than just the plasmon resonance. There's a lot to observe
Sure.
in optical absorption and reflections.
With a particular calculations. We were looking for those plasmons, and this is a very particular calculation out of the response of the material.
If you want to know if your model's right, you should test more than just the plasma.
Well, I mean, this is not a new technology, I would say. This calculation of the dielectric constant or dielectric operator by DFT is something that has been worked on by a lot of people. So this is not a new part of this work. So I want to conclude by a little bit what I'm most interested in, I would say, looking at how we can model electronic transport in these multi-layers. So this is the picture I'm looking at. I have 5 layers, for example, just a random number, because I'm a theoretician, so I'm not looking at a very particular system. What I want to do is look at electrons in the system and how are they moving around, how I can model conductivity or these things. And the very big difficulty here is that the crystal lattices in general do not match. And even if they do, like these 2 layers of graphene, there might be an angle between them. And the result is that the block theory that I was very summarily presenting earlier does not apply. And therefore, we cannot apply DFT. We cannot apply any of the usual tools. We actually don't have a well-defined problem that we can solve. So we had to work a little bit looking at these particular materials at how we can model, how we can understand what is happening here. So the first idea is that there's actually not much coupling between those two layers. Why do we not apply some perturbation theory and look at if we can get some interesting results? So this works out a little bit in some particular cases. The problem is that even this perturbation theory is expensive, and we cannot reach very big cells, and therefore we cannot reach really these interesting regimes where we have a large Moiré pattern. And in this case, we would have to model all the atoms in this Moiré pattern to understand what is happening. This is very expensive, cannot be done by usual techniques. So we have a ladder of models that we can work with. At the atomic scale, we have density functional theory, something that describes really atoms from a microscopic point of view, but cannot be used beyond, say, 1,000 atoms in a unit cell to predict properties or to really understand what is happening. Since we need to actually include maybe 100,000 atoms, maybe 1 million atoms in our simulation, we will actually go up to some reduced models that are called tight binding models, just lattice models where the electron is now, the potential is frozen, but we preserve some of the properties of DFT. In particular, we preserve the quantum character of electrons. They still have an orbital on the face. And this enables us now to go to much higher, much larger cells and simulate things numerically. And then we want to use these models, these reduced models, to actually predict properties. And first of all, understand what is happening. So in a nutshell, a tight binding model is just a reduced model where the electron is allowed to live on points of a lattice instead of just in a continuous model. So that represents the fact that in a reasonable approximation, the electrons are localized on top of the electrons. They occupy specified orbitals. And so the probability of occupying a certain orbital will be given by a wave function, which is just a square integrable function on the lattice. And linear operators in this world are given by just a big matrix. So if we have a wave function over here, then the linear operator, something like the Hamiltonian, is given by such a matrix where we sum over all combination of atoms, even though we really think that as two atoms are far apart, their interaction will be very small. So in a general case, this is very hard to parameterize, but in the periodic case, it's very easy to look at these kind of systems, because actually the only thing that is important is the difference in positions of two atoms, because everywhere is the same. And therefore, a given coefficient of this matrix over here can be just parameterized by the vector between the 2 points. And in particular, the simplest tight binding model we can think about, for example, the Harper model, will include only nearest neighbor interactions. So this coefficient here will be 1 for these such pairs of sites. And then when we look at such operators, they have very nice properties because the product between 2 operators translates into a convolution of such function. A convolution, as we know, is diagonalized by the Fourier transform. And therefore, this is a very nice thing to study. It looks a lot like this block waves I was talking about. And this is very nice. Now, when we lose this periodic structure, we do not have such a description. And therefore, we are a bit lost. We do not have a nice theory to turn to. So this is the case for these multilayer systems. And we need to look at the geometry to understand how things are going to work. So in such a system, when we look from the top, it's a little bit difficult to see what is happening. It looks like a bunch of random atoms. However, actually, we can look at each layer, say that in a Fourier approximation, it is perfectly periodic. So we have a lattice Rj for each layer. And we have for each lattice a unit cell. And now when I look at this picture over here, I can actually see a lot of order. for example, if I want to be parameterizing what type of configuration I'm in, so I'm sitting somewhere in here, I want to know where are all the atoms in this picture. Well, if I want to know where all the red atoms are in this picture, I only need to know where one of them is, because they are periodically arranged. And therefore, if my origin is sitting here, if I know this gamma 1 vector, which is just a vector in this unit cell, then I will know where the red layer is. And so on and so forth. I can also look at where this boron nitride, so gray and green layer is, just by knowing where I sit in this smaller unit cell over here. And so in this case, with a collection of 5 vectors, I know where all the atoms are. So this is this parameterization of a configuration by just a collection of 5 vectors.
So what is capital omega? Is that the direct product of all these unit cells?
So
Is that gamma 1 cross?
omega is, if I take this particular configuration and I translate around space, that's all the configurations I will see. So
I want to know how you're organizing this. Do you have some kind of a notion of a direct product of all these spaces and translations on all these spaces? That's
Right.
underway.
So in the real space over here, if I have an actual sample,
Yeah.
what I'm able to do is I translate all of them together, right? But here, I can, with my mind, translate just one of them.
Right.
And this is what happens when I translate just one of those vectors. I
That's
translate
what I'm asking about your notion.
just a single layer.
Those crosses are some kind of direct product.
Yes, that's right.
Okay.
So it's a collection of a vector in each of them.
Yeah.
And now, just looking at the bilayer, I can think about parameterizing my tight binding model with this kind of approach. So if I am sitting on an atom, which is this red atom over here, then I want to know what are all the elements of my big matrix between two sides. These sides could be either red atoms belonging to the same lattice or blue atoms belonging to the other lattice. So if I have a matrix element between two red sides, this will be this third term over here. And we say that a possible coefficient between these two sides will depend, first of all, on the relative position of these two sides, which is contained in just a single vector over here. And we also possibly depend on the position of the top layer, which is embedded into this parameter gamma 2, which is on the left. So with such a function, I can parameterize all the possible tight binding coefficients between two red sides. And I can do the same for all pairs of such atoms and have a minimum parameterization of my tight binding coefficients. And this is what I want to look at. This is now a complex mathematical object. It's called a C-star algebra. And unlike the periodic case, this is a non-commutative C-star algebra, which picks up a lot of complex tools I do not want to get into. But an important one, which is actually quite physical, is how do we compute actual observables. So an observable means that we have to compute some trace and average it over space. So in principle, if I have an observable represented as an operator f, what I would like to do is take a cutout of my material, look at the trace of the operator restricted to this bond, and as the bond grows, I kind of converge to this thermodynamic limit to the macroscopic average. If I want to do this numerically, this is just impossible because I do not know how much of the material I have to take, and this will depend highly on the parameters. However, in this case, if I know how to parameterize the function, I can take this average very easily by averaging over the space of configurations. So this is a very nice, very implementable method that allows me to take an average of a given observable by just averaging over the space of configurations instead of taking a large cutout of the material. So this is what we hope to do. We also have explicit implementation, explicit formulae that come out from the C-star algebra on how to compute functional calculus. So for example, if I want to know the density matrix of the material, then I need to know how to take a function of the Hamiltonian, and this is where this comes in. I do not want to get into details. And out of this comes a model for electronic transport. So this model was developed by Jean Bélissard in particular, where we have an electric field, and we imagine that we have an electron hopping through this material. So this electron will actually follow something like a quantum Drude model, where for a while this electron follows the usual master equation of the quantum mechanics. So it will just evolve somewhere in this crystal. And then sometimes it will encounter some scatterer, what are very important for this phenomenon. So in particular phonons or other electrons or defects or whatnot. And these will actually now change the wave function in such a manner that over all possible averaging of this, this model, I get a simple Ohm's law where the current is proportional to the electric field which is applied via a proportionality constant which is usually known as the conductivity. So this is the object we are after. This is the object that will be needed to understand the properties of the material. And this object is given by a Kubo formula, which is extended from the commutative case, from the periodic case where we know a usual formula. So in a non-commutative case, we get a more complex looking object, but that includes this trace that I was talking about, this macroscopic average that can be taken by averaging over possible configurations.
So after you've gotten done with all this non-commutative stuff,
Yes.
doesn't this all just map onto some bigger finite dimensional matrix problem, or infinite dimensional matrix problem? Doesn't this all just map into some big space where you have a big matrix to diagonalize?
You can always map it into a big problem. The problem is how big is it and can you put it on a
You
computer,
don't want to map it to a big problem.
right? Yes, but we have equivalence. If we take a big cutout, we know it will converge, but we prefer something that we can deal with. So just to look at what effects we can expect from this incommensurability, let's have a look at a simple toy model where I just look at two chains. So I forget about my two-dimensional layers. I have two atomic chains with two different lattice constants, L1 and L2. And I want to play with these two lattice constants and see what happens when the ratio between them is periodic. The ratio between them is rational number. That means that I have a periodic assembly. When this ratio is going to be irrational, now I have an aperiodic assembly. So what happens when I play with this ratio? So I can normalize this, just taking the product to be 1 to simplify the presentation. I can construct a model Hamiltonian, which is the simplest I can think of. So in each layer, if it were isolated, I would have nearest neighbor interactions where my Hamiltonian has coefficient 1 for two sides that are separated by just a single unit constant. And then between the layers, I introduce something like a Gaussian dependency. So I put coefficients that decay like Gaussian functions depending on how far the sides are. So this is a little bit keeping the idea that if two atoms are far apart, they will not interact. And this actually looks a lot like what we get parameterized time-binding models directly from DFT. So when I compute this, I get this nice plot where on the x-axis, I have the ratio of lattice constants I was talking about. So in particular, for a ratio of 1, that means that I have two layers that are exactly the same on top of each other. So I have a periodic assembly. And what I have in this case is just by the Bloch theorem that the density of states is non-zero on a continuous line. It means that I have a band structure going from minus 2.2 to 2.2, something like this. And then as I go slightly away from 1, so I lose this periodicity. So I translate a little bit. What I see is an explosion of little gaps, something that looks a little bit like this Landau-Lavance that we're talking about. So here also we have a competition between two length scales. And it's interesting to see that the result is similar. We also get a bunch of gaps appearing immediately and something like Landau-Lavance popping up, depending proportional to the difference between the lattice constants. So the main takeaway from this picture, I would say also, is that it's dangerous to make a computation for a small supercell. So say you have a system which is very close to being aligned, like boron nitride and graphene. And for computational purposes, it's easier to tweak them to have a periodic structure, to make them with the same lattice constants. This way you can make a simple periodic one size cell that contains both lattices. And you go like, well, I didn't push too much, so this must be correct, and I will get a nice result. What this picture tells me is if I look a little bit away from 1, I have a very different behavior than if I'm exactly at 1. So just a small difference can make an actual big difference in the overall picture. I don't want to get into too much details, but this conductivity I was talking about can be effectively computed. So this formula is actually expensive to compute, and therefore we take a middle step, which is to compute the current correlation measure. So we can probe with Chebyshev polynomials what happens, and this all works very well numerically. And I get also a plot of the conductivity, which is a little bit keeping the same structure as for the density of states. So again, here I change the ratio of lattice constants. On the vertical axis, I move my Fermi level up and down. And what I see is that I have these gaps where there is no conductivity, and they all originate here around 0. And then I have also satellite pictures that will look like repetitions of this middle fan over here. And that comes exactly from this fractal structure, where if we look at integer values of the ratio of lattice constants, we have a repetition of the same pattern around 1, where if we have a small integer, we have a periodic structure. Moving a little bit away from it gives us an explosion of little gaps. So just to conclude, where do we go with this? So we have introduced these star algebras. This was something that was introduced quite a while back, and that is very theoretical actually, very rigorous, but very hard to get into, and has not been used numerically to predict properties. So we think that this would actually be interesting to look at this from a point of view of numerical computations, to implement this framework, because here it seems to be natural and interesting. And this will make us probably able to predict properties more accurately and faster. However, to really reach the interesting problems, we probably have to include defects, because as was said by Colin Humphreys, crystals are like people, and it's the defects in them that will make them interesting. And therefore, we have still work to do, because we want to include, first, as a simple approximation, some Anderson type disorder where each side gets some random energies, but more realistically, we'd like to look at defect distributions, and the goal with this will be to look at, for example, semiconductors, where we need to dope them in just the right way, and this will give us the properties that are interesting for, say, developing the new transistors. And with this, I thank you for your attention.
So in your bank calculation, you see lots of these gap openings, right? Can you give
Yes.
more physical insight, like why you have this kind of gap opening, and like for example, like for this state right above or right below the band gap, are they some form of periodic wave function, or?
So,
I mean, you have a big
okay,
band gap there.
yes. So the natural way to look at these band gaps is that they will appear because of some large periodicity, for example. We know that we have a large periodicity that translates into a very small Brillouin zone, and that gaps will appear at the edges of this Brillouin zone, which is very small. And so when we are here, especially slightly away from 1, we know that the periodicity would appear at a very large length scales, and therefore we will see lots of little gaps appearing because the corresponding Brillouin zone is very small. The fact that this one is the biggest and survives for the longer, this is probably parameter dependent. I wouldn't be able to really explain why that is. That would be interesting. I think that there should be a way to analyze this pattern exactly like the Hofstadter butterfly, to look at topological numbers appearing in the gaps. And that would be an interesting way to look at it.
So from this model, are there any predicted behaviors that can be studied experimentally?
Well, this is just this simple one-dimensional model. So I don't expect this particular model to be something that can be observed in an experiment, unless one does some kind of artificial structure. But it's interesting in the way that it predicts interesting things to happen as soon as we are close to periodic, but not quite. And so we are looking to compute things in more realistic structures when we have actually two layers, for example, in particular that have a very small twist angle. So this ratio of lattice constants plays here the same role as the twist angle, and we could expect similar behavior, as we saw in this picture I had earlier of the magnetoresistance in these slightly twisted bilayers. Over here, it is the same idea that we have insulating states, so gaps appearing because of the superlattice. So this behavior is general and actually happens in graphene. Yes?
So you mentioned about like from theory modeling of like atomic arrangement of those two material into the heterostructure and towards macroscopically like design of devices, right? So just because I'm a device person basically, so that's why I'm curious on based on your simulation or say some simulation you will do or you're doing. Do you see any, or do you have any suggestions for like newer novel devices that we could consider? Because you know there are lots of publications already on, say, you know, graphene field transistor or diode, or my lab also has made tons of them already. So we're definitely interested in whether theory could have some insight or suggestions on, say, newer properties electronically, optoelectronically, or photonically, that when we kind of stacking the structure in a different way to end up with new physics in devices.
So I would say that that's our fabulous goal. That's our dream. Now in the life cycle of theory and in particular numerical modeling, I think we have quite a bit to go before we get there. So as in this kind of methods, I like to think that there are two main parts. The first part would be to try to get up a model running and try to see if we can already reproduce what's out there and test the theory and whether if it's true. And once we get that going, then we have some hope to predict some properties. And I think we are still in that first cycle. We have some hope to. I have some hope to look at, in particular, topological properties that can come out of this kind of model. And that would be already an interesting prediction if we can make those happen just because of the twist angle, for example. So that's something I want to look at in the very near future. I think Sihuan had a question. Yes.
Can you explain what is the origin of the van der Waals force?
Well, sure. I mean, we have these structures that have, they are 2D structures, so they are by essence stable, and they have their covalent bonds fully full. So there is not going to be electron sharing between these two layers. However, the van der Waals forces, as I think about them, is the fact that the clouds will be slightly polarized between them, and this will give rise to a weak attraction between the two layers.
What type of force between? So what is nature of the van der Waals force between these two layers?
I'm sorry?
What is the nature of the force?
It's the fact that we have these two, the clouds of electrons living on each layer, and they will have some kind of polarization because of the reaction to the other layer. And this polarization results in a slightly attractive force.
So basically you're saying
it's a traditional van der Waals force.
You mean the electron dipole?
Yeah. It's
Dipole
dipole interactions.
Okay, so can you also explain what is the difference between the classical Hall effect and the quantum Hall effect?
So the quantum Hall effect is the effect where we see, at least the integer Hall effect, is the one where we see plateaus that appear at precise quantized values of the conductivity. When we
why is it quantized? So what's the difference between the classical Hall effect and the quantum Hall effect?
Well, the quantum Hall effect appears, is this quantization of the conductivity. So we have this transverse conductivity that appears.
That's appearance, okay? That's why you call this name, but what is the origin? Why is quantized? Why is classical Hall effect? First, what is classical Hall effect? And why is not quantized?
Well, the classical Hall effect, if I'm not mistaken, is the fact that because of the magnetic field, the electrons acquire, if they try to go straight, they will actually start to rotate, and therefore there will be an effective current in the transverse direction. In the case of the quantum Hall effect, it's quite a bit more involved. It's due to the fact that the system gets some topological properties in the gaps. If we look at the Hofstadter spectrum, for example, we know that in each gap we have an integer value, which corresponds to an index in the gap. And therefore, you can show that actually this translates into a quantization of the transverse conductivity as long as the Fermi level is located somewhere in the gap. And it can be localized in the gap because of defects in the material in particular. So it's important to have defects present so that we don't jump straight to the gap, because there are no states in this picture. This is a perfectly no defect picture, and therefore if I were to be an experimentalist and to tune the amount of electrons that are present in my system, I would just jump straight through the gap and never observe any plateaus. But because I have actually defect states that are localized inside here, do not participate to conduction, as I increase slowly the number of electrons in the system, I will actually be for quite a while in this gap where I have quantized transverse conductivity and zero direct conductivity.
So very simple question is, in your definition of the phi zero, the flux quantum is like h over e. Okay, then if you look at the web or whatever, the books, it always says flux quantum is h over 2e. So why, so what's the difference between 2e and e?
I suppose that's just when you take it into account the spin generacy.
Pardon me?
That would be if you take into account spin or not in the picture. So you have double the amount of electrons.
All right. Okay, anyway.
Okay, so thank you very much for your interesting